Welcome. In this session, we'll explore the Hadamard product of matrices. Suppose that we have two rectangular matrices, each one being composed entirely of real numbers, and each one having m rows and n columns. This, we couldn't take in general the product of A and C because the number of columns in A and the number of rows in C might not match. But we can take the Hadamard product. We write the Hadamard product in various ways. One of the most common ways is a circle with a dot in it. Sometimes it's just the circle. We'll always put the dot. And what we'll say is that equals by definition. So what we do is, let's just imagine a small matrix for now. So this is A11, A21, and so on to AM1, and A21, A22, and so on to AM2, and we'll just stop it there. And then suppose that our matrix C is likewise, this is C11, C21, and so on until we've written all of the rows, and then this will be C21, C22, and so on until we've written all of the rows in that column, and this will continue on for a while. The way that we compute the Hadamard product, or it's also called the dot product or the Entrywise product, is that this is, what we do is we just multiply the corresponding entries of the matrix. So entry 11 of the Hadamard product is A1 times C11. So that's A11, C11. The second entry in this column is A21 times C21, and so on. And then the last entry in the first column is AM1, CM1. Then if we were to move to the second column, we would do the same thing. This would be A21 times C21, A22 times C22, and so on until we have written all of the entries in, oh, that's a C, in that column. So another way that this is written is that if we were to call this matrix M, we could write Mij as Aij times Cij. So this extends to matrix vector and matrix 1 form. So let's suppose that we write A in terms of its columns. So that'll be column 1, column 2, and so on until we've written all of the columns in the matrix. Then we could say that if we have a vector that also has m entries, so that is, it's got as many entries as each of the columns of this has, then we could say that the Hadamard product of a matrix and that vector, we could define that as, we could say that this is A1 dot times V. That is, we can treat a vector as though it's an m by 1 matrix. And if it's an m by 1 matrix, we can apply this rule, and we can say that the dot times of a matrix and a vector is the dot times of the vector with the first row, the dot times of the vector with the second row of our matrix, and so on until we have written all of the columns. And so we can get the definition of the Hadamard product of a matrix and a vector just by doing it column-wise. And then similarly, or likewise, we can also define a Hadamard product with a 1 form, and I'll just say likewise. Because what we would do is we would write the matrix A in terms of its rows and then perform the same operation. So some of the simple properties of the Hadamard product are it's commutative and it's associative. So what I mean by that is that the Hadamard product of A and C is the same as the Hadamard product of C and A. And it doesn't matter what order we do this. So if we have 3 matrices, if we have the Hadamard product of A with the Hadamard product of C and M, that's the same as taking the Hadamard product of A with C and then the Hadamard product with M. It also distributes over addition. We have to be very careful with the Hadamard product in figuring out the size of the matrices to make sure that everything works out. So we can distribute this over addition, and the reason is that we're doing it entry by entry, and so that's just the same as each entry's multiplication will distribute over each entry's addition. So the Hadamard product of the sum of matrices is the sum of the Hadamard products. So that is A Hadamard product C plus A Hadamard product M. So caution, I'll write that in capital letters, which I rarely do. Caution when mixing products. That is, that in general, A Hadamard with C ordinary matrix multiplication M will not equal this. The sizes can often be wrong, and you can't take these, you can't perform the distribution, and you definitely can't perform the multiplication. So another thing that we can do is we can rewrite the product of a diagonal matrix and a vector. So let's consider a diagonal matrix produced from a vector, which is the diag operator of the vector, and that equals, what that will look like is that'll be A1, A2, and so on to AM, and that'll be the diagonal matrix. So if we have a diagonal matrix produced from a vector A, and we multiply it by some vector C, that turns out, you can do this math very quickly, is that turns out to equal the Hadamard product of the two vectors. That is, when we do this, if you were to just take A and then you were to write C down here, you would see that this would be A1 times C1 and then all zeros, and then 0 A2 C2 and all zeros. So this is a very quick thing for you to verify. The final property that we may need later in this course is the mixed product theorem. So that looks like this. The mixed product theorem, which is in the language of this course, is a fact because we're not going to prove it. The mixed product theorem is that if we have the Hadamard product of Kronecker products, so we have to have everything the same size. So if we have the Kronecker product of A with C, and then we have the Kronecker product of M with W, and we take the Hadamard product of the Kronecker products, that equals the Kronecker product of the Hadamard products. What does that mean? Well, that means that's the same as taking the Hadamard product, the dot times or entry-wise product of A with C, and then performing the Kronecker product on the dot-wise product of M and W. And we can use these in we can use these linear algebra concepts when we get to multi-layer neural networks, because every now and then we'll see a diagonal matrix and we can replace that diagonal matrix. This is a fairly costly matrix to both store and compute. We can very concisely and quickly store it as a vector and then compute the Hadamard product. And then every now and then we'll have these complicated Kronecker and Hadamard products, and we'll be able to use this mixed product theorem to reduce these to a simpler form.